This is Dr. Sridhar back to you with another video lecture on maximum power transfer theorem and how can we make use of this maximum power transfer theorem to find out the efficiency and other associated calculations like determining the source resistance which is required to transmit the required amount of power to the load. All these things we will discuss in this today's video session with the help of one or two simplest problems. Now, let me take the first problem like find the value of RL, that is a load resistance for the given network below. The network is given here. So, in that one, let me calculate whatever the load resistance RL, and that RL we have to find out such that there must be a maximum amount of power to the RL, or that is a load resistance. That's what the first bit is. And second one is, and also find the maximum power through load resistance RL by using maximum power transfer theorem. So, in my previous video sessions, we have determined the different expressions and the condition for maximum power transfer to the load. And in order to see the power to be maximum in the load resistance, and at that particular instant of time, what is the expression for efficiency? That efficiency is maximum is 50%, already we have ensured, and the efficiency is just 50%. The condition for maximum power is RS is nothing but the RL. What is that RS? RS is nothing but the source resistance. So, internal resistance of the source, and RL is nothing but the load resistance. So, for again, just I am recollecting what is the statement that maximum power transfer theorem. So, the statement of the maximum power transfer theorem is, it states that in a linear bilateral network, maximum power is delivered to the load when the load resistance is equal to the internal resistance of a source. So, the source here it is, that is 6 volts is the voltage source. Now, that voltage source you have to equivalently represent with its internal resistance. And here in this example, if you could see, the 6 volts and 6 ohm is seriously connected here. 6 volts and 6 ohm is seriously connected means you can treat the 6 ohm as the internal resistance of the 6 volts. And sometimes people may ask, no, how we can say that 6 ohm is nothing but it is the internal resistance of 6 volt source. So, in such cases, that may be the combination of 6 ohm resistance and this 6 ohm resistance and this 5 ohm resistance and this 2 ohm resistance. We don't know exactly. So, that is the reason. So, we had to calculate the equivalent of 6 ohm, 5 ohm and this 6 ohm and this 2 ohm, which may contribute some considerable amount of portion in calculating the internal resistance, which is nothing but the source resistance of the 6 volts voltage source. So, that is a major problem here. So, how can we calculate the equivalent source resistance here? Is nothing but, so here again we are going to make use of Thevenin's principles or Thevenin's theorem to find out the RTH, because here if you could see what our Thevenin's theorem explains, that in the Thevenin's theorem, so this is VOC, this is the VOC, or this is nothing but the VTH, which is connected in series with the RTH, and across which that load resistance it will be connected here. So, I am going to reduce this given electrical network into this standard form. So, what is the standard form here? So, in the maximum power transfer theorem also, so finally, whatever it may be the active electrical network, this total active electrical network, you have to reduce into, so this is the RL. So, finally, this electrical network you have to reduce into the standard form. What is this voltage here? VOC. Whether it is VOC or VAC, whatever it may be, this can be a source voltage. Now, this is again connected in series with some internal resistance. That is nothing but that can be viewed as that is the internal resistance of this particular source. Now, finally, coming to this load resistance, this RL is the nothing but it is a load. So, what happens? So, the given electrical network, whatever it may be the combination of resistances, voltage sources, internal current sources, whatever it may be, finally, you have to reduce this electrical network into a standard form. That standard form is nothing but a voltage source in series with voltage source, one internal resistance, and this combination should be connected across the loads, which is none other than our equivalent representation of Thevenin's theorem. So here I am going to reduce this given electrical network into a Thevenin's equivalent circuit. Now in this Thevenin's equivalent circuit, if you could see, what is this? What is this RL? RL is our interested one. We have to calculate this RL such that maximum amount of power to be transferred. So the condition for maximum power is nothing but that source resistance is nothing but source resistance and load resistance must should be same. Then only we can see maximum amount of power that will be transferred to the load. So just now also we have discussed the Thevenin's theorem, equivalent of Thevenin's theorem is required. Now for better understanding, for handy information, we can define the Thevenin's theorem that any linear bilateral network containing several voltages or currents and resistances can be replaced by just one single voltage source, that is VTH, in series with a single resistance RTH connected across the loads. This VTH is nothing but open circuited voltage or Thevenin's equivalent voltage measured between the load terminals, and RTH is the Thevenin's equivalent resistance measured across the load when all the voltage sources and current sources are represented with its internal impedances. That is, voltage source can be short circuited and current source can be open circuited. So this finally the circuit, this type of circuit can be equivalently represented by means of a voltage source VTH and RTH, and in series with this RTH you can see some load resistance. So how can we calculate this RTH? Of course, we have discussed so many times the method to calculate open circuited voltage or Thevenin's voltage and or Thevenin's equivalent resistance. In my previous videos also, once again I am presenting this explanation for better understanding. So what is the method to calculate the RTH? So if you want to calculate this Thevenin's equivalent resistance, it can be achieved by short circuiting the voltage sources in the active network and open circuiting the current sources in the given network. Here only one electrical voltage source is there, that is 6 volts. Now if you want to calculate RTH, first of all you have to bring that load resistance completely away from the electrical network. That is the first step. So you have to keep, or you have to represent, or you have to earmark separately the load terminals, and load resistance should be kept completely away from the network. So you have to finally represent the circuit in two ways. What about the load terminals? That should be completely away from the actual network. So rest of the network you have to keep inside the rectangular box. That is nothing but that may consist of various number of resistors and other passive elements along with the voltage sources. So here I am going to make an attempt to determine the RTH. So I am completely removing the load resistance and I am going to short circuit the voltage source. So 6 volts voltage source is short circuiting, and this RL is nothing but load resistance is completely disconnected from the section. So if you could see here, if this 6 volts voltage source is short circuited, then this 6 ohm and this 6 ohm. So this two comes into parallel. So 6 ohm and 6 ohm are having equal resistances. So the resultant value is nothing but the half of the individual resistance value. So that is 3 ohms comes into picture. And again, if you could see here, this 3 ohm and this 2 ohm comes in series with each other. So 5 ohm, and again this 5 ohm and this 5 ohm comes in parallel. So that equivalently that value is nothing but the 2.5 ohm. So which is nothing but the load resistance. So this RL is equal to 2.5 ohm value. So that actually how I told you that RL is equal to 2.5 ohm, because this RL is nothing but the RTH, that is nothing but the source internal resistance. That value is nothing but the Thevenin's equivalent value, that is nothing but the 2.5 ohm. So next thing is, let me calculate what about the Thevenin's voltage or open circuited voltage. How we are going to achieve this value means just you isolate the load resistance from the section and you have to see the total entire network from the load terminals, then the thing will be VTH. So from this, with respect to this load terminals, just you look back into the circuit. If you could look back into the circuit through the load terminals, that voltage is nothing but the open circuited voltage or VTH. So that open circuited voltage or VTH is nothing but that is the voltage drop across the 5 ohm resistance. If you want to determine the voltage drop across this 5 ohm resistor, that you can achieve by having the current in this particular loop. So this current, and not only this current, we require this current also. So let me calculate, or by apply the KVL, you can do this with the mesh analysis concept by applying the Kirchhoff voltage laws for the individual loops. Then you can easily find out the current in this second loop. Here, this is the first loop and this is the second loop, and the current in the first loop is nothing but I1, current in the second loop is I2, and just you apply the Kirchhoff voltage laws for the first and second loops. So drop across this 6 ohm is nothing but 6 into I1 is nothing but the drop across this element, and drop across this 6 ohm resistor is nothing but 6 of I1 minus I2 current, and this, the sum of this 6 ohm drop and sum of this 6 ohm drop is equal to 6 volts. So that is the expression for this one. So what about the voltage balance equation? This is 6 I1 plus 6 I1. So totally 12 I1. Yes. Minus 6 I2 is nothing but it is equal to 6 volts. So this is the voltage balance equation of your mesh 1 or loop 1. So similarly, if you could come back to the second loop, now this, the drop across this 6 ohm resistor is nothing but 6 of I2 minus I1, because we are working in the second loop. So priority will be given to the second current. So 6 of I2 minus I1, and the drop across this 5 ohm is nothing but the 5 times of I2, and drop in the 2 ohm resistor is nothing but the 2 times of I2. If you are simplifying this, so you are going to get minus 6 times of I1 plus I2 and I3. That is nothing but this is a 13 is equal to 0, because why it is 0 means that is there is no active voltage source is connected in the second loop. So this is directly becomes 0. So minus 6 I1 plus 13 I2 is equal to 0. If you are solving this loop equation 1 and loop equation 2, I am going to get I1 is equal to 0.65 amps and I2 is equal to 0.3 ohms. So by having this I1 and I2 values, I1 value and I2 values, you can easily calculate whatever the VTH or V open circuited voltage. So that VTH or VOC is equal to the drop across this 5 ohm resistor. This 5 ohm into whatever the current in this second loop, that is 0.3. So 0.3 times of 5 is equal to 1.5 volts. So this is the Thevenin's equivalent voltage we measured by seeing back into the circuit through the load terminals. So this same actual network now we can represent in a simplified manner, that having one Thevenin's equivalent voltage source and one Thevenin's equivalent resistance and the load as usually. So VTH is equal to 1.5 and RTH already we have calculated that value is equal to 2.5, and this is load resistance. So what is the condition here? So we have to find that load resistance for the given network for the maximum power, or the power is maximum. So in order to see that power to be maximum, now we have to equate the load resistance equal to the source resistance. So if so, what could be the RL value? RL value and the source resistance, that is nothing but the earlier we have represented this as a RTH, because that was the equivalent Thevenin's value. So that becomes the source resistance of the open circuited voltage or Thevenin's equivalent voltage. So this becomes source voltage, and then this is nothing but RS is equal to source internal resistance. So RS, and then RL becomes RS only, that is nothing but it is also equal to 2.5 ohms of resistance. So this value is 2.5 ohm and RS is nothing but the RL only. So that value is nothing but the 2.5 ohm resistance. So thus we have determined the value of load resistance based on the condition what they have given is here in this problem is we have to find out the load resistance such that the power to be maximum supplied by the source voltage, that is the 6 volts. Now, in this one, now in order to simplify this entire network to this simplest form, the voltage source also have changed its magnitude from 6 volt to 1.5 volts. This is nothing but this we achieved with the help of Thevenin's principle. So next thing is we have to determine the efficiency. So now come back to the second part of the question here. Find the maximum power through load resistance RL by using maximum power transfer theorem. So what is the power expression here? Vs square by 4R. So already we derived this expression for this power value, and power is equal to 1.5 square divided by 4 times of 2.5. Here the thing is, here it is, the Vs is nothing but the open circuited voltage. Now my sincere appeal is, don't go directly to the 6 volts, because 6 volts was there at the initial time, but this total entire network we have reduced into a simplified circuit having only one source voltage, one source resistance and one load resistance. So here we may be confused whether this Vs means whatever the voltage we have to consider to calculate this power. So that voltage is nothing but the Thevenin's voltage, that is nothing but open circuited voltage. We have got this expression by reducing this actual circuit with the help of Thevenin's theorem. So here this, you please be cautious whatever the value we have to consider, whether 6 volts or 1.5 volts. Now once we achieve to this particular circuit means, please ignore this actual network. This actual network only we have reduced into a simplified form. So P is equal to Vs square by 4R, means Vs is nothing but 1.5 whole square divided by 4 times of R, whatever the R now. This R is nothing but the RL or RS. Now, in order to overcome the ambiguity between whether RS to be selected or RL to be selected, that's why now this value is also equal to the R directly. Now R might be RL or RS, because anyhow this expression we achieved by assuming the power is maximum, the maximum power. So that's why this R may be RL value or RS value, it doesn't matter here. 4 times of 2.5 and in the numerator 1.5 whole square. So finally we are going to get the power is nothing but the 0.225 watts. Now, this is the expression for maximum power, and this is the condition for, this is the condition to see that maximum power. So based on this logic only we have determined the value of the load resistance, that is nothing but the 2.5 ohm. Now hope this problem has given good emphasis on maximum power transfer theorem. Thank you for watching this video. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.